Hello guys, welcome back to my channel. And today we're not going to be doing any infinite series, any trig integrals or any high school calculus. We are going to be doing a proof of Legendre's duplication formula. So let's get started without wasting much time, and you learn a lot today. I hope so. So Legendre's duplication formula states that if you have a gamma of k multiplied with the gamma of k plus half, that's just equal to 2 raised to 1 minus 2k power times gamma of 2k times the square root of pi. So this formula is really interesting because, say, if you have a gamma of k, it just multiplies it by 2, so you get twice of the original argument, and that's pretty much like, say, if you have a double angle formula for sine 2 theta is 2 sine theta cosine theta. So if you have values for a singleton angle theta, if you have the values of the sine and cosine of that singleton angle, you get the sine of 2 times that angle. So similarly, it's like the argument is getting doubled every time. So that's why this identity is really special in terms of gamma functions. So how are we going to get started over here? Well, the start is pretty non-intuitive, and I'll have to admit it that, you know, when I was playing with the Gaussian integral a lot, I came across this this initial starting point, and you know, when I just followed some conventional mathematical intuitive steps, I came across proving this. So I accidentally proved this, but now I want to share it with you guys because I think it's really neat. So before starting, I would like to point that the gamma function of, say, a value n, I would like to write the definition of that. The integral form is the integral from 0 to infinity of e raised to negative x times x to the n minus 1 power dx. And this is actually an extension of the factorial. This is n minus 1 factorial actually. It's always that value minus 1. So we have n minus 1 factorial over here. Okay, so now the starting point for this proof is this parameterized function slash integral. So I of t is equal to integral from 0 to infinity of e raised to negative t x squared dt. So you can see that it's pretty much related to the Gaussian integral that I made five different videos to calculate. Different ways of calculating the Gaussian integral. I've made 5 videos on that. You can check them out. So I was playing with this parameterized Gaussian integral. So this is a parameterized Gaussian integral, and we are going to look at this in different perspectives and then equate both the perspectives, and then we actually come across proving Legendre's duplication formula. So let's get started with this. Let's use this thing but have a different perspective. So I'm just going to use this for perspective number 1. Let's do that on a fresh page. See you there. So as I said, we still have I of t, but we are going to look at it in one particular perspective, and then we're going to look at it in another perspective in the second part. So let's do part one now. So I of t is integral from 0 to infinity of e raised to negative t times x squared dx. So this is the parameterized Gaussian integral. So let's perform some u substitution. So let u equals square root of t times x, so that when you square u, you have just this power of e. So du is naturally square root of t dx. So we have upper and lower bounds remain the same because of this linear substitution. With e raised to negative u squared, dx is du divided by square root of t. So we just have our 1 over square root of t times our, well, this is just our Gaussian integral now, right? Well, now if you remember in my last video, the gamma of 1/2 was just 2 times this incomplete Gaussian integral. So it was 2 times square root of pi over 2. So this is basically half of gamma, right? Then if gamma of half is just 2 times this integral is just half of gamma. Please check out my previous videos of calculating the Gaussian integral using the gamma and the beta function if you don't understand how I came across this. But if you want, I'll probably do the substitution for you. So fine, let's do this for now. So if we have y equals u squared, we have dy is equal to 2u du. So we have 1 over square root of t as it is, integral from 0 to infinity, upper and lower bounds as it is, e raised to negative y, and instead of du we have dy over 2 times square root of y. So we can collect the 1 over 2 times square root of t term outside, and we have the integral from 0 to infinity of e raised to negative y times y of to the negative half power dy. And if you compare this to the form of the Gaussian integral, this is just going to be y to the half minus 1, right? So this is basically, by definition of the gamma function, we have 1 over 2 times square root of t times the gamma of 1/2. So I of t is basically 1 over square root of t times gamma of half. So let's just clean everything up now. Fair enough. We found a gamma version of I of t. So now let's differentiate with respect to t. So we have I prime of t, and we have integral from 0 to infinity of the partial derivative with respect to t of e raised to negative tx squared dx. So that translates to basically integral from 0 to infinity of negative x squared times e raised to negative tx squared dx. And the good part is we can express this again in terms of a gamma function. So let's make the substitution y equals tx squared. So we just have dy is nothing but 2xt dx. So dx is dy over 2t, and x is just y over t all under root. So y over t under root, that's basically your dx, and x squared is y over t, right? So we have negative, again upper and lower bounds are the same. X squared is, as I said, y over t times e raised to negative y. Dx is this dy over 2t times square root of y by square root of t. So, well, the t's are just constants, right? So we can just simply pull them out of this integral. So we have this t squared in the denominator, which we can express as t raised to negative 2, and this square root of t in the numerator, which we can call t raised to half, and both of them will add up with each other. And we have the integral from 0 to infinity of, and this will cancel out with this to get square root of y times e raised to negative y dy, and this y, square root of y is y to the half, which can be written as y to the 3 by 2 minus 1. So this is going to be the gamma of 3 by 2. I'm just directly using the definition we have now, minus t to the negative 3 by 2, because negative 4 plus 1 is negative 3 by negative 3, and then divided by 2, times now the gamma, as I discussed. We still have the 2, right? The gamma of 3 by 2. So nice, we obtained another version of, in terms of the gamma function for I prime of t also. So we have negative t to the negative 3 by 2 power divided by 2 times the gamma of 3 by 2. Let's write this in terms of powers. So we have t raised to negative half power divided by 2 times the gamma of half. Fine, we obtained a clean form of I prime of t. Let's go further now. So now let's again differentiate with respect to t. Let's again differentiate I prime of t with respect to t. So we have I double prime of t now. So it's the derivative of this thing, which will be, well, if we differentiate this again we'll have an x squared, negative x squared come down. That negative and this negative will cancel out, and we'll have x squared times x squared, which is x to the 4th, and we'll have this exponential term as it is, e raised to negative t x squared dx. And now interestingly, we can also convert this again into the gamma function, some t variable times the gamma function. So let's attempt to do that again, and after this I'll just generalize everything. So let y equal tx squared. So dy is again naturally 2xt dx. So dx is dy over 2 times x is square root of y over t times this straight t, and everything else is in order, right? Again, limits of integration are from 0 to infinity. X to the 4th is y over t, but the whole thing squared. This is e raised to negative y. Dx is dy. Well, the 2 is a constant, divided by square root of y times this will just become square root of t, right? This will cancel out with one of these. So now we have half of, we can bring the square root t's outside again. So we have t to the negative 2 power, and minus half, and then inside we have integral from 0 to infinity of e raised to negative y. We have y squared, so y squared minus half dy. So this is basically y to the 4 minus 1 by 2, so 3 by 2, which can be written as y to the 5 by 2 minus 1. So this is gamma of 5 by 2 basically. We just look at this term, which is alongside this -1. So we have half of t to the, this is also going to be -5/2 times the gamma of 5/2. So that's also nice. We found out a small compact version for this. So this is t to the -5/2 divided by 2 times the gamma of 5/2. Nice. Now it's time to generalize everything. Okay, we found the first derivative of I of t with respect to t, then the second derivative, and we can continue doing this process until the nth derivative of I of t. So I want to represent it this way. So that is going to be integral from 0 to infinity of, well, now notice that for the first derivative we had a square, for the second derivative we had a fourth power, for the third derivative therefore we'll have a sixth power, and for the nth derivative we will have x to the 2nth power. Okay, but notice that this negative is also alternating, because next time that you differentiate this you will get a negative x to the sixth power. So this negative is also alternating based on the derivative. So for the first derivative we had a -1, for the second derivative there was a +1. So this -1 will be raised to the nth power, because when n is 1, or when we have the first derivative, it's -1 to the first power, which is -1. That's why we have this. And for all order derivatives, for third derivative, fifth derivative, seventh derivative, we'll have a negative sign, and that fits with everything else. And e raised to -tx squared will be as it is, because it's an exponential term dx. But now notice we're again having this alternating sign part. So -1 to the n, this denominator 2 was remaining a constant, but now notice the power of the t. So for the zeroth derivative we started with the -1/2, and then we just kept subtracting 1, right? For the first derivative we subtracted 1, so -12 minus 1 is -3/2, and then for the second derivative we subtracted -2 from -12. That's why we obtained -5/2. So for the nth derivative we would have to subtract -n from -12, and that will be raised to that will be the power of t, and whatever was the power of t was basically the gamma function, right? But the positive of it. So we have the gamma of the positive version of this, or n plus half. I hope you follow my train of thought, because it's pretty logical. If you analyze all these three conditions of I of t, I prime of t, and I double prime of t, you would basically come to this conclusion in generalizing for an nth derivative. Fine, this is our first perspective now. Now it's actually time to look at I of t in another perspective, and then in the end we'll just club everything together. So I just want you to remember this particular relation for I of t, and that would be really helpful. So in perspective number 2, I have I of t again, which is defined as integral from 0 to infinity of e raised to -tx squared dx, and if you remember correctly, that was just equal to t to the -12 power divided by 2 times the gamma of half. And if you remember correctly, gamma of half was just 2 times the integral from 0 to infinity of e raised to -x squared dx. So it was half of the Gaussian integral. So 2 times Gaussian integral. I've made 5 videos on that. Please check that out. So this we can use directly from my previous videos. Is square root of pi over 2, especially from 0 to infinity. If it were negative infinity to infinity, it would just be square root of pi. So in any case, we obtain square root of pi for this. So I of t is basically t to the negative half power divided by 2 times gamma of half, which is nothing but square root of pi. Fair enough. So just like we differentiated this integral using the Leibniz rule, we are going to differentiate again, but we are going to differentiate this function. So all else we can forget. So let me just erase everything so that you don't get confused. Okay, so when we differentiate this I prime of t, basically this is going to be half will stay out, square root of pi by 2 is a constant, will stay out, and we have the derivative of t to the negative half. So we can just use the power rule of differentiation. So if square root of pi by 2 times we can bring the power down, negative half, times t to the half, and we subtract the power with 1 from 1. We subtract 1 from the power. So we finally end up with negative square root of pi by 2 times 1 over 2 times t to the negative 3 by 2 power. We can do this for I prime of t too. So we have to differentiate this again with respect to t. So we have negative square root of pi over 2 times this existing half times, we bring the power down, negative 3 by 2 times t to the negative 3 by 2 minus half. So this all will just evaluate to this negative, and this negative will cancel out. We have square root of pi over 2 times 1 over 2 times 3 over 2 times t to the negative 5 by 2. This is 1, sorry. 3 by 2 minus 1. I'm doing the product, I'm doing the power rule wrong. So t to the negative 5 by 2 power. So now if we want to generalize for an nth derivative of I of t, that is just going to be, well, we again have this alternating component, right? So for the first derivative we had a negative, for the second derivative we had a positive. So for even derivatives there is a positive, for odd derivatives there is a negative. So we can write negative 1 to the n, just like our previous perspective, times the square root of pi by 2 is remaining a constant. But now notice that for the first derivative we had 1, and for the second derivative we had 3 in the numerator. So for the nth derivative we would have 1 times 3 times 5 times 7 till say the nth odd number, because notice that in I prime of t we had 1, in I double prime we had a 3 in the numerator. So it's accurate to say that this is, so in the numerator we have all the odd terms until what derivative we have, the odd number of the derivative. So for the second derivative we keep on multiplying all the odd numbers until the second odd number. So we keep doing that for until the nth odd number for the nth derivative of I of t, and we are going to have this denominator, we have only are going to have a 2, right? So we're going to have n 2's, so 2 to the nth power. And the interesting part is this, the power of the t. So originally I of t had a half power, and we just kept subtracting for every derivative. So for the second derivative we subtracted 2 from half. So for the nth derivative we would subtract n from half. So we have negative half minus n for the nth derivative. So now let's represent this in a better way. So if I to the nth power, negative I to the nth power times square root of pi by 2 times, this is just the product from k equals 1 to n of 2k minus 1 divided by 2 to the nth power times t to the negative half minus n. So you can check this this notation with each of the special base cases that we had of I prime, I double prime and all that. So consider, so for n equals 1, so for the first derivative we had k equals 1 to 1, so 2 times 1 minus 1 or 1, and that's exactly what we had in the numerator, right? Exactly had a 1 in the numerator. And so for n equals 2, or the second derivative I double prime, we had k equals 1 to 2. So for k equals 1 we have 1, for k equals 2 we have 2 times 2 minus 1 or 3. So 1 times 3. That's exactly what we have. So for an nth derivative this makes sense. So the nth odd number is basically 2k minus 1. Or basically 2n minus 1 in our case when k equals n. Fine. So now this is the nth derivative of I of t. So now remember that in both perspectives we obtained the nth derivative of I of t, and since both perspectives are we can equate both perspectives because both of those perspectives arised from this I of t, and I of t was identical in both cases. So it's time to actually equate both perspectives. It's time to equate the nth derivative of t expression for both perspectives. So let's go ahead and do that now. So from perspective number 1, we obtained that negative 1 to the n divided by 2 times t to the negative half minus 1 times the gamma of n plus half is equal to the nth derivative of I of t. From the second perspective, we obtained that negative 1 to the n by 2 times square root of pi times the product from k equals 1 to n of 2k minus 1 divided by 2 to the nth power times t raised to negative half minus 1 is also equal to the nth derivative of I of t. So it's time to equate these two, right? So equating these two, we have negative 1 to the n divided by 2 times square root of pi times product from k equals 1 to n of 2k minus 1 divided by 2 to the n times t to the negative half minus n is equal to this thing, negative 1 to the n divided by 2 times gamma of n plus half times t to the negative half minus n. Now notice that all these crazy worrisome terms are going to cancel out. So now all we are left with finally is an expression of gamma of n plus 1 half being equal to square root of pi divided by this 2n that remained times this product from k equals 1 to n of 2k minus 1. And let's remember what this product was. It was the product from the nth of all odd numbers till the nth odd number, which was 2n minus 1, right? When k equals n, that's the nth odd number. So it was essentially 1 times 3 times 5 times 7 times 9 times till say 2n minus 1, right? And there is a pretty neat notation to represent this. So we call that, this is almost a factorial, but it's not exactly a factorial. It's like a semi-factorial. So we can represent all of this by using this notation, 2n minus 1 double factorial. You can call this a double factorial or the semi-factorial, it's up to you, but I'm going to actually explain, and we are actually going to find a better expression for 2n minus 1 double factorial, and then we are actually going to be complete with our proof by the end of simplifying this double factorial. So I'm going to explain briefly what the double factorial is on a fresh page. Let's get to it. See you there. So now notice that a double factorial of any number is basically a sort of alternating factorial, right? So we have, say, n times n minus 2 times n minus 4 times, say, n minus 6, so on. So we can represent this as the ordinary factorial, but we have to divide out these n minus 1, n minus 3 is basically these other terms that were, because the factorial has a factorial now, has all these terms, right? N times n minus 1 times n minus 2 times n minus 3 times n minus 4, so on. But we don't want this term, this n minus odd number terms. So we'll have to divide them out of the regular factorial, right? If we want to define the double factorial or the semi-factorial in a new sense. So that's just going to be n minus 1 double factorial, right? Because say n minus 1 double factorial is going to be n minus 1 times, you skip n minus 2, which is the next in an ordinary factorial, and you have n minus 3, and then you have n minus 5. So it's basically a product of those odd terms that you wanted to avoid, that you wanted to actually divide from an ordinary factorial. So that's one way of actually doing this. But let's take the case where n is even. So n is of the form 2 times k, where k is any positive integer. So n double factorial basically is just going to be the product of even terms, right? So it's going to be 2 times 4 times 6 times 8 times 10 times, and say that goes on till say n was 2k, right? So this goes on till say 2k, because n is 2k. So now let's factorize a 2 from all these things. We have 1 times, we factorize the 2, so we just have 1. Instead of 4 we have 2, we have a 3 here, we have a 4 here, we have a 5 here. And that goes on till k, because we removed this 2 from the 2k. So, well, 2 from each term, and there are k terms, so 2 to the k for each term. And what is this? That's just the regular factorial, right? So n double factorial when n is even is just 2 to the k times your k factorial. So if you had say 5 even terms, this would just be 2 to the 5 times 5 factorial, right? So that's the case for n when n is even. Let's look at the odd case now. So now the case where n is odd. So basically n is of the form 2k minus 1, where k is some positive integer. So using this definition of the double factorial, we can write that odd n double factorial as just a regular n factorial divided by n minus 1 factorial. But now let me remind you that if n is odd, n minus 1 has to be even, right? Because take any odd number. This is like the number before it has to be an even number. So you can take 3, number before it is 2, which is even. This is true for any odd number. So n minus 1 is always going to be even if n is odd. So what do we know about, sorry, this is a double factorial because of this definition. What do we know about even number double factorial? We just have this nice relation of them, right? So if n is of the form 2k minus 1, we can just substitute that 2k minus 1, the whole thing factorial, divided by, since n minus 1 is going to be even, we're going to have, well, we can just use this formula for an even n of 2 to the k times k factorial, right? And you can check that this holds for any k. So if you have k equals 3, or let's take a smaller number. Say let's work with 3. So if we have, say say this is basically the third odd number factorial. So 2 times 3 is 6 minus 1 is 5 factorial divided by 2 to the third power times, well, this is 3 factorial over here. So this is 5 times 4 times 3 factorial by the property of factorial. This is 2 to the third times 3 factorial. So the 3 factorials are going to cancel out. We have 5 times 4, which is 20, and 2 cube is 8. So this is going to be well, 10 by 4, which can be written as 5 by 2. And that was basically 2k minus 1 double factorial, right? So factorial until 5. So we have 1 times, basically fifth odd number. So 1 times, I'm really sorry guys, I made a mistake here, a silly mistake. This is not 2k minus 1, it's just 2k factorial. And you can well, check with 3 now, because say you had when k is 3, you just have 5. So 5 times 2 is 10 factorial. Rather, sorry, when this is 2k, right? So this is 3 times 2 is 6 factorial, and we have 8 times 3 factorial. So this is 6 into 5 into 4 into 3 factorial divided by 8 times 3 factorial. So 4, and this becomes 2, this becomes 3, and this becomes 15. And say we had to calculate the double factorial manually instead of using this formula. This will just be 2k minus 1 double factorial, or 5 double factorial, which will basically be 5 times 3 times 1, basically all odd terms. So this is going to be 15 again. So basically that's verified now. So it's basically the 2k minus 1 is an odd number, so its next number 2k is even. So you start the factorial from that, and then you remove that excess number, because that's why we have a k factorial, because that even double factorial will go up till 2k, and because we have to cancel out that terminal 2k that we um, introduced in our formula. So this is basically your formula. I'm sorry for making some calculation errors. I can really mess my calculation sometimes. So we are exactly you going to use this formula now in to simplify our nth derivative of t expression that we obtained by equating two perspectives. Because if you remember, we had a 2k 2k minus 1 term there, 2n minus 1 term there. So let's go ahead and do something about that. So we had the gamma of n plus half to be square root of pi divided by 2 to the n times 2n minus 1 double factorial, and we know that this is odd, right? That's if you remember our in perspective number 1 and 2, we always had an odd series. I think that was perspective number 2, yeah. So in perspective number 2 we had odd powers, right? 1 times 3 times 5, so this is always odd. So, and what did we learn from the entire discussion on double factorial is there is a formula for this, right? So we can just write 2n factorial divided by 2 to the n times n minus 1 factorial, right? Because this is the entire term factorial divided by even double factorial. So let's simplify stuff further. We can break this factorial into 2n times 2n minus 1 factorial divided by, just have a 2 to the n term here. We can break this up as, sorry, this is just n factorial, right? That's the even term factorial. The double factorial basically can represent it in this way. We can break this up into n times n minus 1 factorial. And notice the good part that the n's cancel out. We can use some properties of exponents. We have 2 to the n, and over here we have 2 to the n minus 1, and we have a 2n minus 1 factorial divided by n minus 1 factorial. And what is all this equal to? Basically it's equal to the gamma of n plus half. So I would actually like to regroup some terms with gamma of n plus half being equal to, we can bring them in the numerator. So we have 2 to the 1 minus n plus n, 2n, 1 minus 2n, and signs flip when we take them in the numerator, times square root of pi. And remember this identity of the gamma, how is the gamma function related to the factorial? So n minus 1 factorial is basically gamma of n, so you just add 1 to the expression that was in the factorial. So if you add 1, you just have 2n, you have gamma of 2n divided by, again add 1, you have gamma of n. Now I would like to take the gamma of n on that side. I have gamma of n times the gamma of n plus 1 half being equal to 2 to the 1 minus 2n times square root of pi times the gamma of 2n. And if you just look back at what we had to prove, that's exactly what we had to prove. So hence proved QED. We've proven Legendre's duplication formula. I hope you enjoyed this video, and please excuse I'm saying sorry for all the goof ups. Please excuse me for those. I'm just really sometimes really bad at computation and stuff. So that's it for this video. I would like to say please like, share and subscribe to my channel. Recommend me to all your math friends, or I don't know, even math teachers. This is basically recreational math. You can enjoy yourselves. Please follow me on Instagram. I have this username. I post math art. I'm going to expand in the future a lot. So meanwhile, stay safe. Peace out. Have a great day. Ciao.